Alright, silly people, here's the situation. We've got a couple of matrices, A and B, and identical to the last problem, we're going to figure out if these are diagonalizable, and then find the eigenvalues of A and see if the eigenvectors of A match those of B. So just going ahead and saying that yes, they are diagonalizable because, again, all Hermitian um, matrices like this uh, are actually diagonalizable, and so by Hermitian I mean that if you take the Hermitian conjugate of either of these, you're just going to get back out the same matrix, and that's because A, they're real, so they are actually just equal to their transposes. Um, and yeah, every row, just going row by row and column by column, the rows matches the columns. So these are both Hermitians, so we can keep going. They are diagonalizable. Next, we have to check if they commute. That is, the commutator of A and B equals 0, or in other words, AB minus BA equals 0, or in other words, AB equals BA. So let's just calculate AB and BA separately. So AB is going to be 2, 2 minus 1, 2 minus 1, 2 minus 1, 2, 2 times 2 minus 1, 2 minus 1, 5 minus 1, 2 minus 1, 2. Just multiplying these guys together. 4 uh, minus 2, and then also minus 2. And then 4 plus 1 uh, plus 4, and then minus 2 uh, minus 2 plus 4. Interesting. And then minus 2 plus 10 plus 1, and then minus 2 minus 5 minus 2, and then just going to be minus or plus 1 uh, plus 10 minus 2. And then it's going to be 4 minus 2 minus 2, 4 plus 1 plus 4, and then minus 2 minus 2 minus 2 plus 4. Yeah. So all in all, this is going to be 0, 9, 4. No, not even 4 there. 0. 9, minus 9, 9, 0, 9, 0. Slick. Okay. BA then is going to be 2 minus 1, 2 minus 1, 5 minus 1, 2 minus 1, 2 times 2, 2 minus 1, 2 minus 1, 2 minus 1, 2, 2. And just doing, oh no, doing that multiplication. We have 4 minus 2 minus 2, so we're already looking very similar. Minus 2 plus 10 plus 1, 4 minus 2 minus 2, 4 plus 1 plus 4, minus 2 minus 5, and then minus 2, 4 here, and a minus, or a plus 1, and a plus 4, and now minus 2, minus 2 plus 4, 1 plus 10 minus 2, minus 2, minus 2 plus 4. Alright, so this is, yeah, this is the same. It's 0, 9, 0, 9, minus 9, 9, 0, 9, 0, for sure. Now we have to actually diagonalize A. So setting up the characteristic equation then, we're doing the determinant of 2 minus lambda, 2 minus 1, 2 minus 1 minus lambda, 2 minus 1, 2, 2, and setting that determinant, or actually, forgot there's also a minus lambda on the bottom right thingy there, and setting the determinant equal to 0. So we've got 2 minus lambda times minus 1 minus lambda times 2 minus lambda, minus 4 minus 4 minus 1 minus lambda, minus 4 times 2 minus lambda, minus another 4, 2 minus lambda. Set that to 0. So let's write it like this: 2 minus lambda all squared times minus 1 minus lambda, minus 8, that's going to turn into plus 1 plus lambda, and then we've got minus 8 times the 2 minus lambda term. Set that to 0. Let's expand this, so it's going to be 4 minus 4 lambda plus lambda squared times minus 1 minus lambda, 8, or minus 8 plus 1 is actually just minus 7. And we've got the plus lambda. This turns into minus 16 plus 16, nope, plus 8 lambda. That equals 0. Expand again. Now we've got minus 4, minus 4 lambda plus 4 lambda, and then plus 4 lambda squared minus lambda squared minus lambda cubed, minus 7 plus, or okay, so minus 7 minus 16 turns into minus 23, and then 8 plus 1 is 9, so plus 9 lambda, right? Let's try to put it all together. Minus 4 minus 23 is minus 27. This cancels this out, so we all have just plus 9 lambda. 4 minus 1 is 3, so 3 lambda squared, and then minus lambda cubed. And that's going to make our polynomial. This is actually factorable if you take the form that you have right now and you try to factor out a 3 minus lambda from it. And what you get is lambda squared minus 9. And I'm going to check that real quick just for sanity purposes, because you get 3 times lambda squared, so 3 lambda squared. Then you get 3 times minus 9, so minus 27. And minus lambda times lambda squared makes minus lambda cubed. And then minus lambda times minus 9 makes plus 9 lambda. So yeah, that's a good factor. Then we can, I'm actually going to divide by minus 1, which is a perfectly legal move, and just flip the sign of the first of those because it's cool and funny to do it that way. And then you factor the quadratic term because it is just a difference of squares. You get lambda minus 3, lambda plus 3. So you have lambda minus 3 squared times lambda plus 3, which means you do have at least 2 eigenvalues, which are 3 and minus 3. But then you also have an additional 3 because you've got lambda minus 3 squared. So yeah, it does end up being degenerate in its own space, but that's fine. Finally, we can find the eigenvectors from this. So again, A was 2, 2, minus 1, 2, minus 1, 2, minus 1, 2, 2. We can multiply it by an arbitrary vector, which I'm going to call A, whose components are A1, A2, and A3. and on the right hand side it should be equal to 3 times our arbitrary A vector, like this, right? So just going through the multiplication, we've got 2a1 plus 2a2 minus a3 equals 3a1 for the first equation. And then let's just work with this for now. So we're going to have 2a2 minus a3 equals a1, very simply. And then let's do the second equation, which we get from the eigenvector equation even. So 2a1 minus a2 plus 2a2 equals 3a2. Just adding an a2 to both sides and plugging in what we just got for a1, we have 2a2 minus a3, and then plus, it's supposed to be a 3 there, but 2a3 here equals 4a2 on the right hand side. So we have 4a2 minus 2a3 plus 2a3 equals 4a2, and all of these actually cancel out, which means a2 and a3 end up being free variables, and a1 is dependent on either of those. So let's pick the simplest sort of choices that we can make. Yeah, let's just pick the simplest ones. We'll pick that a2 and a3 are both just 1. And so then a1 will be 2 minus 1, so just 1 again. So a is 1, 1, 1, and then the normalization for it just ends up being 1 over root 3 if you care. And so that's A. Then we need to find the eigenvector B via the same process. 2, 2 minus 1, 2 minus 1, 2 minus 1, 2, 2 times arbitrary eigenvector b1, b2, b3 is equal to minus 3 times b1, b2, b3. Setting up the equations again, we've got 2b1 plus 2b2 minus b3 equals minus 3b1. This time, let's move the b1 stuff to the other side and have 5b1 equals b3 minus 2b2, and then solve for b1 to get b3 minus 2b2 over 5. Cool. The other equation from the eigenvector equation that we've got up there is 2b1 minus b2 plus 2b3 equals minus 3b2. And let's just add a factor of b2 to both sides. So 2, then b1 was b3 minus 2, b2 over 5, right? So minus, or just plus 2b3 equals minus 2b2, right? Let's multiply the entire thing by 5, so we get 2 times b3 minus 2b2 plus 10b3. That's actually going to end up being plus 4b2 plus 10b3 equals minus 10b2, and then simplify a little bit to get 12b3 equals minus 6. And again, this is a minus sign. I keep making mistakes. But yeah, you get minus 6b2 if you do it all correctly on the right-hand side. So simplifying, minus 2b3 equals b2, and now we can pick what we want b3 to be, and then b2 and b1 will follow. So let's pick 1 for b3, and then we'll follow that b2 is minus 2, and then 1 plus 4 is 5, divided by 5 you get 1 again, so b1 is also 1, and then the normalization for that ends up being 1 over root 6 if you care, but that's the second eigenvalue for the vector A, or eigenvector even. Um, Finally, we need to check if either of these happen to be simultaneous eigenvectors with the matrix B. So let's just stick the vector A next to B. So it's going to be 2 minus 2, or 2 minus 1, 2 minus 1, 5 minus 1, 2 minus 1, 2, times, what was it, 1, 1, 1, with a normalization of 1 over 3. And then we'll call the uh, corresponding eigenvalue for the matrix B just L1. And then it's also multiplying our eigenvector 1 over 3 times 1, 1, 1. The normalization stuff cancels out, and then the left-hand side turns into the vector 2 minus 1 plus 2 minus 1 plus 5 minus 1, 2 plus, or actually minus 1 plus 2 equals L1 times 1, 1, 1. And just carrying out the math in the left-hand side, we end up with 3, and then 3, and then 3. So solid. Yeah, this is certainly an eigenvector then of the matrix B with eigenvalue 3. Moving right along, we'll stick the vector B next to the matrix B to check that it ends up being another eigenvector. So that was 1 minus 2, 1. On the left-hand side, we'll put it equal to L2 over root 6 times 1 minus 2, 1. And again, the normalization pieces cancel out. And on the left-hand side, carrying out the matrix multiplication, we get 2 plus 2 plus 2, and then minus 1 minus 10 minus 1, 2 plus 2 plus 2, as compared to the just L2 times 1 minus 2, 1 thing. So then just doing the arithmetic in there, 6 minus 12, 6 on the left-hand side makes this straight up is an eigenvector, just with L2 equals 6. So yeah, no need to check if a linear combination of the eigenvalues form up another eigenvector. I'm sure it does anyway, though. All right.